Thank you. Thank you, Imager, for having the office available. Yeah, around 2 o'clock every day, I kind of get bored, so I'll just kind of crank up Imager and just kind of cruise through it. So I completely know what you guys do, and it's awesome. Keep it up. So what we do at Compose is we run databases for customers. Those databases, we started off with MongoDB. We ran MongoDB for 3 years, and then we started to build out our platform to really diversify what kind of databases we run. What MongoDB does well is that it does replication well, particularly at the server level. So what MongoDB does well is replication at the server level, really primary, secondary, failover, all that stuff just kind of happens seamlessly with MongoDB. So when we first started talking about Postgres, that was one of the benchmarks that we had to have, one of the features that we had to have with Postgres. And we're going to talk about how we got etcd running with that. If you don't care what I say and you're just like, just show me some code, I have a TLDR right here, and there's a place that you can go and monkey with some code. I'm completely fine with you cranking up your laptops, going in there, have fun with it. It's actually going to be a lot of the code that we talked about in this, and it was working earlier today. So, okay. I'm Chris Winslett. I'm at Winslett, so I work at Compose.io. I was a high school teacher for 2 years out of undergrad. So no matter what happens during this presentation, we can keep pushing through this presentation. Like, lights go out, I'll be fine. I'll just keep talking. We'll keep rolling. If anyone has any questions, just raise your hand, and I'll answer your questions. You can even shout it out. I may tell you, hold on a second. So we'll just keep rolling. So when we started using Postgres, so you think, OK, these guys were running MongoDB. Why did they start running Postgres? We started running Postgres because we had a financial analysis project. We needed to know what was happening at our company. And it wasn't exactly easy for us to get that data out of MongoDB, particularly doing data exploration. So what we did was we found MoSQL, which was written by Stripe, and we pumped that data out of MongoDB into Postgres. From there, we could actually start doing joins. So we've actually been running Postgres for a long, long time. And we've been querying Postgres for a long, long time. So as we made our product and as we expanded our infrastructure to run multiple types of databases, one of the things I wanted to run very, very quickly was Postgres. So it seems my slides here are faster than my slides there. So I was talking about this one, but it should be. OK, we're good. Our database product, our platform performance, MongoDB. Yeah. So we actually run MongoDB, Redis, Rethink, and Elasticsearch now. We also run Postgres now. It is still in beta. You can come and use it. What it does is these databases scale automatically. So as you begin using this database, start small, you grow bigger. Your database will automatically get more resources. You don't have to think about how which plan you fit into. You don't think about how you have to migrate it or anything. So what you do is you come in, start using your database. We give you more resources, give you more RAM, more CPU, more I/O as you add data to your database. So our database product. The question was, can we run Postgres on this same kind of platform? Because the other database that we're talking about with Redis and Elasticsearch and MongoDB, these are kind of new age databases, or they've been written in the past 10 years. And we knew how they behaved. Also, they're a lot simpler than Postgres is. Postgres has a lot of years of code built into it and just the way it behaves. So we had a lot of questions about that, too. And then we had operational requirements. Those operational requirements were that it is replicated, highly available, no human interaction for failover. We don't want, running databases for customers, we don't want to wake up in the middle of the night and have to press a button for someone to continue using their database. We want things to happen automatically. Also, we want to minimize core engine modifications. One thing we don't want to do is create caveats for our customers. So we don't want our customers to use things and then find a caveat based on some type of modification that we made. So we try to minimize the core changes to the database so that customers can truly use the database. So that was the operational experience, the operational requirements. the customer experience, we want people to just use Postgres. We want people to experience an entire deployment from Postgres, so be able to create multiple databases, be able to use the tools that they expect in their Postgres. So we didn't want to abstract away the Postgres experience at all. So come in, start using Postgres. Failover mechanism requires no code changes on their end. So what we didn't want customers to have to do, just like our ops guys, we don't want them to have to get up and push a button to failover. We don't want our customers who are running their Postgres with us to have to get up and change something on their application to continue using a high available system. So it's we want them to continue using, their application to continue using the system as it should. So that's kind of drinking out of a fire hose, but that's like the things that we had to have for Postgres to be able to work on our system with our customers. And for us, so that we could run it effectively. So we start, one of the first things we did, so what I'm doing is I'm kind of building the case for how we came around to etcd, to using an etcd system to manage the state of Postgres. And then what we did after we laid out these parameters was we investigated some tools. RepMGR with pgpool was kind of the going thing for Postgres replication and high availability. What we found is it required a human interaction for failover. You had to actually go in there and say, I want you to failover now. Also, the resyncing, there were kind of some issues once you failed over following the new primary. And it does not use Postgres streaming. It uses SSH streaming, so there were some other conventions. Also, pgpool is flaky on failover. Like, it would work that first failover. You failed over again, it would stop working. So there was kind of some back and forth there. So that was kind of the thing that you found when you kind of went and searched Postgres high availability. Next thing was streaming replication came out in 9.1 for Postgres. Streaming replication is awesome. Basically, you can say, take your secondary Postgres over here, tell the wall log for everything that happens on that leader, and you have it in sync. But that's Postgres core functionality, and Postgres core functionality is quite naive. Like, all it does is just the syncing. Like, there's no failover. So there's no automated failover. It's just the replication. There's no changing, like redirecting a customer to a new Postgres. So this was one of the tools that we could use. Oh, excuse me. This is one of the tools that we could use. Then another one was bidirectional replication. This is master-master. This appears to be where the Postgres community is going in the future, some type of bidirectional. There are commits to a patch out there, and it looks very promising. The problem is it runs on a per database model. So per database, per cluster. So that would mean if a customer spun up a cluster, they would only be able to use that one core database. They wouldn't be able to use the entire Postgres deployment like they would expect. Also, it requires a patch on the core engine, and we didn't feel comfortable putting that patch on the core engine because we didn't know the caveats that would come up or the bugs that it would create. And we weren't comfortable with the amount of support that we would get from that patch. So we found this. In the long run, this may be the way that Postgres kind of ends up, but in the short run, it was a little bit too risky for us. So then we had to ask the question, is automated failover with Postgres too ambitious? Like, if no one else is doing it, or very few other things are doing it, should we attempt it? And at that time, we kind of kicked around the idea of, well, a customer can come in, click on a button, choose to fail over their Postgres, or they could do this other thing, and it would automatically fail over. And in the end, we decided against that. That would actually create more of a support issues for us, particularly with customers coming to us and saying, hey, my database is down. It's like, well, you've got to go click this button. And so that created that was enough for us to continue down the path of trying to find something. So what we learned from the tools investigation, what we learned from the tools investigation is that Postgres cannot manage its own its own canonical state. Like, it can be a leader, but it shouldn't be telling everything else that it's a leader, because there's no consensus. Like, Postgres, the streaming replication is asynchronous. We could do synchronous replication. We'd potentially forfeit some performance with that. So we shied away from that because we wanted better performance. So what we did is Postgres could not be the canonical source of data for its own state. So we looked at surf, we looked at console, we looked at, you pronounce it etcd, right? OK, that's the way I've always pronounced it. Just wanted to make sure. So we looked at surf. It's not consensus-based, so that would be out. We looked at console, and it runs with consensus, and it actually has a lot of really nice tools. And then we looked at etcd, and we actually, in the beginning, decided for console. So what we did was we built a prototype for console. Console has a lot of really nice features. It has locking, it has sessions, and it has health checks. Actually, with the sessions, you can't take out a session lock unless you have unless you have a system that passes all the health checks. So what you have to have with console, which is really nice, is these health checks that say, yes, this Postgres is healthy enough to become primary. And it was good. So it worked out well. The console was running there next to the Postgres. We had one console per Postgres in the deployment. So if we had like a 3-member deployment, we'd have 3 consoles running. Those consoles were connecting each other, letting everything else know how healthy it was, that kind of stuff. It was good. And we actually built a, so when I built a little prototype code, there's a Python module there, the console HA. There's a very tight coupling in this console module, very tight coupling between the console interaction and the HA decision loop. And that's OK. I mean, it was very much our early prototype phase. And this is the ultimate diagram that we came up with. So here's what happens whenever a deployment starts. So deployment starts up there. And then we have capsule starts. And then governor starts, which is a Python script that we're running. And then we check if the data directory is empty. And then we go through this entire initialization process. So what you see here are like this route over here is an initialization process. This route over here is a state manager for Postgres. You don't have to memorize this. Just look at it, acknowledge that it's complex right now. And I'll show a nicer, prettier one later. That we just did through iterations. And so this was the first console diagram. This is the second console diagram, so it gets a little bit more complex. This isn't a fault of console. It's just kind of some of the iteration that we had. So console results, it was amazing. It automatically grew and shrunk as you added new members to console. Health checks to prevent unhealthy secondaries from acquiring locks. It was really nice. There was a good flow. Until there wasn't. And we found the critical flaw. Like, it worked great in prototyping. So console, it's excellent, as long as you're not running it the way we needed to run it. And so what we needed to do was run console along with every single Postgres. So what happened was we'd have a lot of consoles on a box because we run multi-tenant database machines for customers. If we had 100 Postgres on a box, we'd have 100 consoles on that same box. And then that became each console took out a 40 gigabyte swap allocation, a virtual memory allocation. So that's fine for prototypes, not for production. Like, you start loading up a server, and it hit a wall pretty quickly. It would actually stress the CPU on that, and then stress the network in between processes. It was actually quite interesting. So what we added to our requirement that we had earlier, the operational requirement, was that we needed something lightweight. So what we found from console was that HA Postgres is possible, but we needed a tool that uses the resources more wisely. So we're in the database. We run databases for customers. So if we're allocating this much, if we're unwisely using our resources such that we had this just wasted resources on a machine, then we can't take that and sell it to customers. So it was basically a pretty big issue for us. So the module that I showed you earlier that I'd written for console made it pretty nice. There was a very tight coupling between the two. Because of what we learned in console, we could switch to etcd in about a day. And that was just kind of saying, OK, the pattern for console looked like this. The pattern for etcd looks like this. Both of them had HTTP requests. So we did HTTP requests. So they have HTTP API. So basically, we changed out the console API for etcd. Now, this is the modern etcd diagram that we have. So it starts, it runs through an initialization process. The same runner has a running loop. If you went to the GitHub repo that I posted earlier, this PDF is actually in there. So you can actually look at a detailed version of it. And then there's actually code that does this particular process within that same repo. So what we used etcd features for, of course, we use the consensus. That comes out of the box. I mean, etcd is built with RAF consensus protocol. And then Postgres does not have consensus, so that's why we said it's not its own state manager. Then the features that we use in the API are recursion, TTL, previous value, and previous exists. And what these make, I'll kind of describe how we're using each one of these. So recursive, whenever a new Postgres member boots up, the runner boots up, what that runner does is it contacts etcd and says, here I am, here's my IP address, my address, and my port to connect to my Postgres, and here is how you can refer to me. Here's my domain name. So then we have the TTL. So we use the TTLs within etcd as a keep alive. So as a leader's Postgres is running, as the Python script is running that, it will continuously write to a keep alive key on TTL that is a definable TTL length. Now we use previous value along with TTL to make sure that the TTL key does not change when we write to this lock. So what we say is like Postgres 0 is leader. I want to extend the TTL key for Postgres 0 as long as Postgres 0 is still the value. So that's what that previous value does. Now, previous exist, we use this to initialize a deployment. So imagine you have a lot of Postgres coming up in the beginning. There's going to be a race to initialize. So this race to initialize, we have to define which one is going to be the winner. This pre-value, or pre-exist, if you just put previous exist false, it will say if this is no value, then whichever one wins this gets a 200 response back, not a 412. So whichever one gets this response back, that one needs to go ahead and initialize their database. So because of these iterations, we removed the tight coupling in classes. So we had tight coupling between the HA decision process, which was some of the decision tree that you saw, and actually how you would interact with the state manager, or the state information. So we decoupled it into these 3 different pieces. So with the code that kind of you guys have access to now that's on GitHub, you can actually take this and replace any one of these components. Like if you wanted a Postgres, or if you wanted a Redis handler, you could have a Redis handler. Or if you wanted if you wanted a Redis state interaction thing, then you could have a Redis state interaction class. And then the HA decision loop is the thing that runs these things. So issues with etcd. The issues with etcd weren't as big as the issues with console. It is overly aggressive about consensus for our use case. We had to tone back some of that with tuning. So it was using a lot of CPU, particularly when we had a lot of them on the box. We toned back the, what's the? Heartbeat. Heartbeat, yes. Yes, so we lengthened the heartbeat. And so once we lengthened the heartbeat, it improves CPU performance. There's more instructions here. Like if you just go to etcd performance in Google, it'll take you straight to this page and give you a lot of good reading. So these aren't really issues. It's designs with etcd that were issues coming from our previous assumptions having worked with console. Like console was nice because it would expand and contract its members and just kind of go about its day. etcd doesn't do that, but that's OK. We really don't need it to do that because we don't have the concept of those health checks being directly associated with the state manager anymore. We took the health checks out of the state manager, which was being run in console, and put them into our runners. And so once we took that out of there, it kind of became, it wasn't that big of an issue. So as long as we have an etcd that can handle the state for deployment, then that's accessible, highly available, then we can do what we need to. OK, time for a demo. Does anyone have any questions yet? OK. Let's see. OK, here's the code that I was talking about earlier. So if you just go here, if you have the proper things installed, you can basically just copy and paste, and it'll come up and start running this. We've even got a proxy config. So you've got your. So what I was talking about earlier with pgpool, pgpool, it didn't handle state well after 1 or 2 failovers. Proxy is really good at that. There's some code in this proxy status sh to kind of show you how to do how to use proxy with Postgres. So let's see what happens. OK. So if you come here. Oh, hey, we're all ready. OK, so etcd. So you can get etcd on Mac pretty easily. You just go brew install etcd, and then you have access to it. It's really nice for kind of quick prototyping and stuff like that. When I was writing a lot of these components, I just kind of ran it locally. So this is going to be our state. So etcd is up and running. Now so what I've done with these Postgres YAML files, let's see if we can see it better over here. So here's a Postgres 0 YAML file. So what we've done here is we have a loop wait, so that kind of defines how often our HA loop runs. And then we've got etcd scope. And then we have a TTL for our etcd, which we've set to 30 seconds. We also have our etcd host. So as you go through all this, you can kind of modify it. We have this name for this node. So it's called Postgres 0, Postgres SQL 0. Then we have the listen, what we want it to listen to. We have data directory. Then we have some replication information that we're going to need for Postgres to set up its streaming. And then we have some parameters here for Postgres that we're going to run from the command line. So we're going to do run Postgres 0. OK. So that happened really fast. But let me kind of walk through what happened here. This actually won the race this quickly with etcd. So in order to, let's shut that down so we can actually see how fast it goes. Let's blow air data. OK. So let's start up 2 Postgres runners real quick. And what's going to happen is these things are going to sit there and wait on etcd. They are not making decisions until etcd is available. Postgres cannot handle itself. So what's going to happen is these scripts are waiting and waiting and waiting. And they're just kind of queuing. Is etcd ready? Is etcd ready? Is etcd ready? And then once we start up etcd, one of these will win the race. That one won the race. This one could not yet connect to that one because it's not up yet. So that one is now the leader with the lock. And then this one is ready to accept read-only connections. So what happened in this is that this one won the race. This one became initialized. The runners that I run this with have actually connected to etcd, used the preexist faults to win the race. Then it used now it's using the TTL to keep the TTL up to date. the key that's been defined by the code there. Any questions? Okay, so now this is a real test. We're going to shut one of them down. Okay. Let's see, let me get some HA going. Okay. 3.3, cool. Such are her proxies. Proxy, okay. So are her proxies running, service unavailable? Okay, now it's available, so it's up. Her proxy is running on port 5000. Okay. PSQL, yeah, port 5000. So we're connected through her proxy. A proxy properly routed us to our primary. Create database bat layer. Okay, connect bat layer. Okay, and then create table users ID serial. And then name varchar. I'm sorry that my typing is so much worse than it usually is. I'm working with one finger down. Okay, so insert into users value. Name, values, Steve. Okay. So now we've got this, and then let's take one of the hosts down. So this one is the secondary, this one is the primary, we're going to kill it. The replication is no longer running here, no copy in progress, it was killed with a end of line, or end of streaming message. And so what happens is, we're waiting on that TTL key to expire now. etcd still has that TTL key out that was being updated by the primary that was previously running. And so once that TTL key expires, what's going to happen is the primary, or this one will become primary. So lock owner is Postgres 0, which was this one. I am Postgres 1. Come on. OK, so now what happened is the runner for this Postgres actually took over the lock. So it took over the lock. Once it took over the lock, it promoted it. You can see the entire decision tree right here under helpers, and then under HA right here. So this is the decision tree that it runs through every couple of seconds, however long you tell it. So the state handler is going to be the Postgres state handler. You can specify that state handler. And then basically you check if the leader is unlocked. And then you check for healthiest node, where the state handler goes out and says, hey, am I indeed the healthiest node that I know about? So basically what I do with Postgres is like, I've got all the members because we registered the members when the runner came up. So what it does then is then it goes around to all the Postgreses that it knows about and says, hey, tell me where you are with your wall file. Tell me where you are with your wall file. Tell me where you are with your wall file. And so what it can do is it can measure that wall file position to see exactly which one is the healthiest. So then it just walks through all these. If you're interested in this kind of stuff, you're interested in how etcd kind of works like that.
How far down have you taken the timeout?
You mean the TTL?
Yeah, what if I took it down to a sub-second?
I don't know, try it. Yeah, what we run at now is, what we run at internally is 30 seconds. So we actually, and that's what we tell our customers. There will be, we run 30-second TTL. So once a member recognizes that another member is not available, it could be up to that long.
Do you have an experiment in how far down you can take it?
I've not. Yeah, yeah, different use cases are different ones. Like, that's one thing that I'm kind of saying about this project is like, we define, like we have a description about how our Postgres runs that we want our customers to read, and that we tell our customers, here's how our high availability runs. This is a template. Like, we really aren't to the point. We can't just go out and say, everyone should be running their Postgres like this, because everyone has their own certain requirements, kind of like what you guys have. So, I'm assuming that you guys need those microsecond, like TTL.
So it's a trade-off.
Yeah, yeah. No, we haven't. We haven't toyed with it. So let's see what happens if we bring this Postgres back up. So what we do with the Postgres is we actually start Postgres as a secondary to come back online. And we have it actually follow 169.0.0.1 so that it won't find any other Postgres. And then we bring it online as a secondary, and then we can actually talk to it and see how healthy it is, and then try to get it back into a healthy state. These are just some errors from the run py file. And so then if we kill that one more time, this other one should take over. And oh, wait a minute. So since we actually, so there now proxy actually pointed to the proper Postgres. So that's proxy with etcd backend. Go look at the code, mess with it. There's a lot of settings, and I tried to extract all the settings into these YAML files right here as much as possible. All right. Any questions? Shoot.
The Python runner is just being executed on the host, or are they containerized in some way?
They are containerized, yeah. So we run one per Postgres. So it's directly associate one-to-one with Postgres. Yeah. Go ahead.
I think I missed your analysis of the perf problem with console. You mentioned it grew to like a 40 gig VM at that time. I mean, like, what was the deal? Were you guys just stuffing a lot of crap into the key value store, or what?
No. Is it? I don't know. There's actually an active issue. Here it is. Is that it? Yeah. So there's actually an active issue. Well, it just allocates the virtual space for this immediately on start. Yeah. Yeah, and
That's something for last year.
yeah. And yeah, so I mean that's just what they've chosen to do. And it's not an issue with console. It's probably as much an issue of like this is how we wanted to run it, and it just didn't match our use case.
I apologize if this has been answered already, but do you have to worry about divergent timelines?
We do. So we have a the best use case for that, or the best way to create a divergent timeline, is to connect with to fill up the connection space with super user connections, so that our runners and health checks cannot connect to it. And so then once you fill that up, then Postgres keeps running along its way, and it actually tries to offload it promotes another member. And so Postgres just keeps running until you kill it after it loses its TTL connection. Yeah, so that absolutely. That is an issue. What we've done here is we've actually done the proxy connected to the Postgres to check the status of the Postgres is in recovery. What we're looking at to try to get around that with a divergent timeline. So that's only been created. We've had this issue whenever customers have filled up that connection space. We haven't had that issue in another scenario yet. So what you're looking at to get around that is to actually do the proxy connection to Postgres based on the leader that is in etcd. And we think we can minimize the space of time there where we have divergent timelines. In real world use scenarios, we haven't run into this yet. It's mostly just us hammering it and trying to get it to break and seeing what we can do with it. So yes, and in those scenarios, what happens because of the divergent timeline? So once Postgres has a divergent timeline, like let's say you fork off and go to timeline 4 and you were on timeline 3, the primary that was there has written more to the wall log than where 4 forked off from it. And so what happens is it can't go from its current position over to 4, so it just gets locked up and crashes and continuously crashes. What you have to do is, basically just say, was any of your writes important over that amount of time, and usually just archive it and delete the data that changed and go about your day. Yeah. Yeah. So go ahead.
How many instances of etcd and Postgres are you running in a typical thing? Are you using one etcd cluster for each deployment of Postgres, or how do you do that?
We do run one etcd cluster for each deployment of Postgres. So we're probably going to be changing that in the future. What you see in this code, so we have our own code that we run for our internal stuff, and it has a lot more like if etcd fails kind of stuff, exception checking. But what we've done in this is we've actually namespaced each of the state managements for Postgres within the HTTP API. And because we've namespaced it, we're going to be looking at kind of having more of a global etcd that gets owned by multiple deployments rather than running one etcd for deployment. But right now, in the foreseeable future, it's one etcd per deployment. Excellent. Thank you so much.